Welcome. The Egyptians of ancient times were very practical people, and they're very practical in their mathematics. So what I want to talk about now is Egyptian fractions and how they approach them, how they approach fractions in general. So let's start with a very practical problem. Suppose we have, say, 7 pies, and we'd like to share them among 12 boys. Now we would say, okay, just give every boy 7/12 of a pie. Maybe chop each pie into 12 bits and give each person 7 pieces. The Egyptians wanted a little bit better than that. They actually asked themselves, okay, what's the best thing we do? Could we give every boy an entire pie? Well, no, there's not enough pies there. Can we do the next best thing? Maybe half a pie for each boy. And we can certainly do that. So let's pull off 7 halves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, I meant 12 halves. There's 12 halves. We can certainly give each boy a whole chunk of pie as big as a half. There at least 1 pie left over. What can we do that? We're still going to share that amongst the 12 boys. I guess now the obvious thing to do is divide that into 12, which I think I've just failed to do because I can't do fractions apparently. And basically we're going to say give every child half a pie and 1/12 of a pie. They say that's better than giving small little pieces of 7/12. Give them as best they can. It's a nice practical result, plus the next best thing you can do, which is 1/12. So today we call any fraction that's written as a sum of fractions of this form, namely with numerators of 1, an Egyptian fraction. And the Egyptians actually had special notation for reciprocals of numbers. They placed a dot on top of their symbols for the numbers themselves. Of course, they weren't using these Indo-Arabic numerals here. All right, so the Egyptians would say, okay, if I wanted to say 3/10, they wouldn't write 1/10 plus 1/10 plus 1/10 because that's not as practical in the sense of giving people the biggest pieces possible. They'd say 3/10 is actually a quarter of the pie for each person plus a 20th of a pie. So they actually had the added rule that they wanted each fraction with the numerator of 1, and they wanted all the fractions to be distinct, coming from taking the largest pieces they can hand out. And it's actually a bit tricky finding these things. 5/7, for example, is a half plus a fifth plus a 70th. And they're actually not unique. I bet, a little exercise for you, you could actually create a different way of breaking 5/7 as a sum of distinct unit fractions. And this little exercise, go for it. So what I'd like to do now is go to a question that actually Fibonacci asked some 2,000 years later in 1200. Does every number actually admit an Egyptian fraction expression? Can you actually do this for each fractions? Now, the Egyptians didn't seem to question this. They had tables and tables of values of how to write each number as an sum of Egyptian fractions. But whether it can be done for every single fraction is actually worth asking. Fibonacci, it appears, is one of the first people to actually ask this and, more important, answer it. So Fibonacci said yes to the affirmative. He managed to figure out a way to prove that every fraction can indeed be written as a sum of Egyptian fractions. And it's today called Fibonacci's greedy algorithm. And I'll explain why the word greedy is appropriate in just a second. Let me illustrate with an example. Suppose we wish to write 4/13 as an Egyptian fraction. Now, the first thing you ask is, what's the biggest amount of pie you can give each child? So we've got 13 kids and 4 pies. And the way I personally ask that question, I can divide the numerator and denominator each by 4. So 4 divided by 4 is 1, 13 divided by 4 is 3¼ That tells me, this is just bigger than 3, that 1/3 of the pie is too big. I can't give each kid 1/3 of the pie. The next best thing I do is give each kid a quarter of the pie. So I'm going to take what I have, 4/13, and see what giving a quarter of the pie out leaves me. Okay, so that's going to be 16/52 for the first one, and the other one's going to be 13/52. That leaves me 3/52 of pie remaining. A division problem of sharing 3 pies amongst 52 kids. We will now attack the same problem the same way. 3/52, bad handwriting, divide top and bottom by 3, 1 and 17⅓. This tells me 1/17 is bigger than 3/52. So the best thing to do is work with 1/18 as the next best choice. So let's look at 3/52 and I'll subtract from it 1/18. Seems a very mysterious algorithm. Cross multiplying, getting common denominator and all that. That's 54 over 52 times 18, I don't know what that is, minus 52 over 52 over 18. That gives me 2 over 52/18. I can simplify that a little bit. It's 1 over 52 times 9. It's basically 520 minus 52. I think that's 1/468. And I think we're there. I can piece this all together and now have that 4/13 is, I was managed to be able to take for a quarter. That left me a result which I could then rewrite as taking off an 18th. There's the 18th. But what that left me behind taking off an 18th is 1/468. There it is, 4/13 is an Egyptian fraction. So Fibonacci realized if you take this process of always removing the largest fraction with the largest denominator you possibly can, you will always end up results with smaller numerator. For example, we started with the numerator 4, we took off the largest fraction we could, and we left with the numerator 3. From 3/32, numerator of 3, we took off the largest fraction we could, 1/18, and we left with a numerator of 2, which actually, I'm just reducing here, left us a remainder of 1. So you get a remainder of 1, that means we can repiece everything together again and write it as a sum of fractions with the numerators 1. That is an Egyptian fraction. So here goes. Let me now prove that Fibonacci's method is always going to work. So let me just do this abstractly now. So the claim is, let's choose a green pen this time. If I'm given a fraction a over b, my job is to choose a fraction 1/nth with n as large as possible, so that 1/nth is still smaller than a over b, but if I went with 1 over n minus 1, it wouldn't work. It'd be bigger than what I can do. So then we're going to subtract from this 1/nth, and the claim is this will produce a fraction with even smaller numerator. Alright, well let's work out this fraction on the left. Let's common denominator of bn, so it'd be a times n over bn minus b over bn. So we've got to check two things. That this numerator is, well, first of all, it better be positive, because if I start going to the negative numbers, I'm in trouble. So we should check it's positive, and we should also check that it's smaller than what we started with. That is smaller than the numerator a. Alright, two things to go through. Well, the thing is, look how we chose this value n. Let's unravel this first inequality. This is telling me that b is less than an, which I could say is that an minus b is bigger than 0. Bingo! Exactly what I wanted. We're still in the positives. If I unravel the second inequality, it's telling me that b is bigger than an minus n. That is, an minus n, an minus b. Oh, I want to say it's not one, that's an a. Gosh, you can see I'm very human. I can't even do basic algebra. This is telling me that an minus b is actually less than a, just as we wanted. So there we go. Fibonacci did this algebra essentially, managed to prove that if you take off the largest value of n you can as the denominator of a unit fraction, you're left with another fraction with a smaller denominator. Repeat the process, you'll be left with a smaller denominator again. Repeat the process, smaller denominator again. As we're staying in the integers and always staying positive, we must eventually end up with a denominator of 1, in which case we can piece it all back together again and end up with an Egyptian fraction expression for the original fraction. So there it is. And you see why it's called the greedy algorithm now, because what you're doing is taking off the largest fraction you possibly can. You're being very greedy, which is exactly what the Egyptians were doing in the first place. It's a very practical answer to their problems. All right, thanks very much.